This video presents a Hello World example of AI transformer in C, C++, and CUDA. Billy will first explain to you the principle of AI transformer and its implementations in C, C++, and CUDA.
Neural networks process numbers, not words. To bridge this gap, language must first be converted into numerical code, a process known as tokenization and embedding. Tokenization is the process of taking the input text and partitioning it into small, secure, manageable units called tokens. These units can be words, phrases, subwords, punctuation marks, or characters. One token is about 4 characters or 3/4 of an English word. Or 100 tokens are approximately equal to 75 words. Embedding is a process of representing tokens as continuous vectors in a high-dimensional space, where similar tokens have similar vector representations. These vectors, also known as embeddings, help AI and machine learning models capture the semantic meaning of the tokens and their relationships in the input text. Embeddings are organized in a matrix form. For example, if a vocabulary consists of 10,000 tokens and each embedding has 300 dimensions, the embedding matrix will be 10,000 times 300. The initial hurdle was that early models processed these numbers independently, ignoring a core truth of language. Meaning emerges from relationships and word order. The following 2 sentences that have identical words demonstrate the point. A dog bit a man is mundane news. A man bit a dog is a sensational headline. For decades, the central challenge of language AI has been how to effectively model these intricate relationships and orders between words. In 2017, Ashish Vaswani et al. Published a milestone paper entitled "Attention is All You Need," presenting the transformer for addressing this problem. The paper improves upon other research results to effectively correlate words with similarities. The main contribution of this paper is that it presents a procedure where many operations could be done in parallel. A transformer is a neural network architecture that processes sequences, text, tokens, data, using a mechanism called attention, which draws global dependencies between input and output. The model looks at all positions in a sequence and decides how important each other position is when computing the next representation. Transformer neural networks are the foundations of ChatGPT and some other popular AI engines. This block diagram shows its architecture. Each input token looks at every other token and decides how much attention to give it. The transformer allows for significantly more parallelization and can reach a new state-of-the-art in translation quality after being trained for a relatively short time. In the transformer, we take every token and passes it through the network to produce 3 values: Q for query, K for key, and V for value. As its name implies, Q is used for searching other related tokens. Comparing Q and K, if Q and K are close, there is a relation. Here, we discuss a simpler case called scaled dot product attention. The input consists of queries and keys of dimension D. We compute the dot products of the query with all keys, divide each by square root of D, and apply a softmax activation function to obtain the weights on the values. In practice, we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as this formula. Here, Q is the query matrix, the key matrix, and V, the value matrix. D is the dimension of the K matrices. Actually, in our discussion, all matrices, Q, K, and V have the same dimension. To find the attention matrix A, we first calculate Q times the transpose of K and divide each of the product matrix element by the square root of D. We then feed each resulted element to the softmax activation function to obtain the attention value. The product of A times V is the output matrix. The output values are passed as input to the next layer, after going through a feed-forward network. The error or loss gradient is used to update the weight matrices, WQ, WK, and WV. Let's briefly review matrix multiplication to better understand the attention formula. This figure illustrates the multiplication of matrix A by matrix B. Each element of the product matrix A times B is computed as the dot product of a row vector from A and a column vector from B, as shown in the formula. For matrix multiplication to be defined, the number of columns in A must equal the number of rows in B. In this example, A is a 4 by 2 matrix and B is a 2 by 3 matrix, so their product is a 4 by 3 matrix. The transpose of a matrix A is obtained by swapping its rows and columns, as illustrated in the figure. So, to compute the product of matrix A and the transpose of matrix B, we simply take the dot products of the row vectors of A with the row vectors of B. For example, the dot product of the first row of A and the first row of B produces the first element of the resulting matrix C. Note that the dimension of A times B transpose times A has the same dimension as A. The dot product of two vectors reflects their correlation or similarity. For example, consider two unit vectors in physical space. If they point in the same direction, their dot product is 1, indicating that they are highly similar. If they are perpendicular, their dot product is 0, indicating no correlation. If they point in opposite directions, their dot product is -1, indicating that they are oppositely correlated. Therefore, the matrix multiplication in the attention formula captures the similarities between tokens. This figure shows an example of matrices Q and K. The dot product of their first row vectors is 2, indicating that the two vectors are similar. In contrast, the dot product of the second row vectors is 0, indicating no similarity between those vectors. Moreover, as discussed in an earlier video, matrix multiplications can be performed in a massively parallel manner. The attention outputs are not used to update the value matrix WV, but the gradients derived from them during backpropagation are. The value matrix is a learned parameter that is updated only during the backward pass, just like any other weight matrix in the network. In the standard self-attention mechanism, that is, the scale dot product attention, we have three key matrices for each input: query, Q, key, K, and value, V. They are created by multiplying the input embeddings by their respective learned weight matrices WQ, WK, and WV as shown in this figure. The value, V, matrix is the source from which information is aggregated. It holds a transformed version of the input. The attention weights decide how much of each value vector to blend into the output for a given token. During the forward pass, the weight matrix WV, which produces V, is unchanged. It's a set of fixed numbers for that specific forward computation. The attention output is a weighted sum of V, but this operation does not change the WV matrix itself. The output is passed to the next layer. During the backward pass or training, the loss gradient or error flows back to update all the weight matrices including WQ, WK, and WV. So while the attention output doesn't directly modify weights like WV, it is crucial for generating the gradient that will modify them. Note again that the weight matrix WV is a learned, static parameter matrix. The matrix V is a dynamic, input-dependent projection created using WV. We can have an analogy by thinking of the value matrix as a library of books. The query is our topic of interest. The key is the library's catalog or index. The attention mechanism uses the query and key to find a list of the most relevant books and how much of each to read, corresponding to the attention matrix A. The output is the specific blended summary we create by reading selected portions from those relevant books. Crucially, writing our summary, that is, the attention output, does not change the contents of the books in the library, the weight WV. However, if we were the librarian and our summary was graded, the error, we might later decide to rewrite some of the books. Update WV via gradient descent, so that future students can create better summaries more easily. The discussions are summarized in this table. The value matrix V is a projection of the input, used as the source for the weighted sum, not updated during the forward pass. The value weight matrix WV is the learned parameters that produce V from the input. It is updated during the backward pass of training via gradient descent. The attention output is the weighted sum of V, providing the gradient for updating. The weight matrix WV. This is a simple demo transformer in C++. Here are some auxiliary functions. The ReLU, rectified linear unit, activation function is used in the feed-forward network. It is a simple, defined as a function that outputs the input if positive and 0 if negative, as shown in this figure. It offers computational efficiency. This is the softmax activation function, which applies to every element of a matrix. This function, matmul, computes the multiplication of two matrices. It returns the product matrix. This function, transpose, computes the transpose of a matrix and return it. This function random weights generates some random weight values for the input matrix W. This class Hello World transformer does the task of computing the self-attention output for given matrices Q, K, and V. Its private function scaled attention is a straightforward implementation of the attention output formula. It calls the external function mulmat to do all the matrix multiplications and return the final output matrix. The public function takes Q, K, and V as input matrices and calls the private function, scaled attention, to compute the attention output. The keyword auto is a type specifier that directs the compiler to automatically deduce the type of a variable. The external function print matrix prints out a matrix. The main routine here presents a demo of its usage. The number of tokens or sequence length is set to 3 and the embedding dimension is 4. In practice, these numbers could be very large. It creates a Hello World transformer object with these values. This is a sample input vector X for demo. It calls the function random weights to create weight values for the 3 matrices WQ, WK, and WV. It then calls matmul to compute the matrices Q, K, and V and prints them out. It then calls the self-attention function of the transformer object to obtain the attention output matrix and prints it. Using the attention output matrix, and a matrix W1 which consists of some random demo values, we create the Z matrix. Feeding the Z values into the ReLU activation, we obtain the output matrix of a simple feed-forward network, and we print out this matrix also. The following presents the corresponding CUDA implementation of the C++ AI transformer up to the self-attention output. Instead of using standard vectors, dynamic arrays are employed to represent matrices. Many of the arithmetic operations are executed in parallel by CUDA threads, resulting in a significant acceleration of the computations. We have discussed CUDA threads previously. This figure provides a concise review of the CUDA thread hierarchy. In CUDA, threads are organized into blocks, and blocks are organized into grids. The dimensions of a grid are specified by griddim.x and griddim.y. In this figure, griddim.x equals 4, meaning there are 4 blocks in each row, and grid dim.y equals 3, meaning there are 3 blocks in each column. Each block within the grid is identified by its indices block x.x and block x.y. In this example, block x.x equals 2 and block x.y equals 1, indicating that the block is located in column 2, row 1 of the grid. Within each block, individual threads are indexed using thread x.x, thread x.y, and thread x.z, while the block's dimensions are given by block dim.x, block dim.y, and block dim.z. In the implementation, we define the macro idx to index an element I, j of a matrix or a two-dimensional or A of row length m. The kernel function matmul performs matrix multiplication, multiplying matrix A of dimension n by m with matrix B of dimension m by r to produce matrix C of dimension n by r. The computation is carried out by n times r threads running in parallel. Each thread computes the dot product of one row of A and one column of B, and stores the result in the corresponding entry of matrix C. The kernel function transpose performs the matrix transpose operation, fetching an element at row I, column j of matrix A with dimension n times m, and stores the result in row j, column I of matrix B with dimension m times n. The operation is carried out by n times m threads running in parallel. The kernel function softmax is a row-wise softmax function that computes the softmax values of one row of element of matrix A with dimension n times m. N threads run in parallel to work on the n rows of matrix A. The kernel function scaling simply divide each element of matrix A by the scaling factor AQRD. N threads run in parallel where n is the total number of elements in the matrix. Random weights and print matrix are two host helper functions, which are the same as those implemented in the C++ program. The main routine carries out the routine work of allocating device memories for computations in the GPU. It follows the same sequence of executions as the C++ implement, but it omits the last step that feeds the outputs to a feed-forward network. At the end, it frees the device memories after copying the data back to the host memories. Let's copy and compile these programs.
Let's first copy the C++ program. So we copy this, and we place this into the transformer.cpp file, okay, and we save it. So we compile this, so we get the output, the executable, it out, so we can execute this. So these are the QKV embeddings, the inputs, and this is the output after self-attendance, and this is the output after the feed-forward network, okay, after the activation function. Okay. So some outputs are 0. We can try again, because the ways input are random. Okay, so the outputs here are different. Now we can comment this statement out so that the output will be a constant. So we compile this again. So we execute this. Now it's always the same, okay, because we don't use a random seed. Now let's copy the CUDA program. So we copy and paste it into this file, transformer.cu. Okay, and we save it. Okay. we have commented out the random statement, so the output should be the same as that from the C++ program. Now let's compile this. But, I think that we missed the I here in the copy. Okay. Okay, now let's try again. Okay, so it compiles and we execute this, so we get the same output. These are the same outputs as those from the C++ program. We didn't do the last part, the part after the feed-forward network, okay? But other outputs are the same. So this wraps up our introduction to CUDA and AI for this year. Thanks for your continued support. We wish you a Merry Christmas and a Happy New Year. We may see you again next year. Bye.